All physical matter in the universe is made of atoms, and we know this because now we can see individual atoms with microscopes. The middle of an atom is called a nucleus, and some nucleuses give out invisibly small, energy-carrying particles we call radiation. Matter which does this giving out of radiation is described as being radioactive. Why do we care? With this invisible stream of energy, radioactive materials are incredibly useful. Read through all the stuff in the list. And that's just some of the uses. Imagine you've ordered a burger in some place. Now everyone is fine with a bit of salad in the burger, but let's say that today you've got just an enormous mountain of salad on top of that burger, maybe even so much that it's spilled over on the side. So what you do is just get rid of most of it, maybe dump it on another plate or something. This is what alpha radiation is all about. If the radioactive nucleus just has far too many particles in it, protons and neutrons, to be stable, the nucleus will kick out a bundle of 2 protons and 2 neutrons, so the nucleus gets smaller. Just like you dumping a load of your salad. Another situation with your lunch might be that whilst the quantity of salad is not too much, unfortunately in the salad is cucumber, which as everyone knows, is completely minging. So you chuck out these bits. Or maybe the salad doesn't have cucumber in, so you think, huzzah, no minging bits. But then, to your horror, you find bits of gherkin. So they get flicked out too. In radioactive nucleuses, if there are just a few too many protons, like cucumbers, or if there are just a few too many neutrons, like gherkins, the nucleus turns one into an electron and flicks it out. Just like you do with salad. The fast-moving electron is called a beta particle. Finally, without stressing about the salad, the burger will probably be sitting there, giving out heat, and heat is not particles. Similarly, a radioactive nucleus may give out gamma radiation, which is just a high-energy, invisible form of light. A drink can carry a certain amount of alcohol, like those blue wickets you're all on when you have mad teenage raves. Similarly, there are particles which carry an amount of something called electric charge. It's difficult to have a picture in your head of this stuff, but unlike with alcohol, where alcohol is just alcohol, electric charge comes in 2 types, positive and negative. This has nothing to do with good or bad, or anything like that. It's just what the person who discovered charge called them, rather than type 1 and 2, or A and B. An example of a particle which carries positive charge is a proton. An example of a particle which carries negative charge is an electron. Particles which don't carry any charge are said to be neutral, and neutrons are an example of this. Because alpha particles have 2 protons, an alpha particle has a size 2 charge, and it's positive. Of course, there are 2 neutrons as well, but they don't have any charge to add. Because a beta particle is a fast-moving electron, it has a size 1 charge, and that's negative. Gamma radiation, being light, doesn't carry any charge. So why are we banging on about electric charge so much? It's because the amount of electric charge something is carrying decides how interactive that particle is with the surface atoms of something it hits. And why on earth do we care about how interactive that particle is with the surface atoms of something it hits? How interactive a radiation particle is with the surface atoms of a material it hits decides how deep into the material that radiation goes. What with each alpha particle having a size 2 charge, alpha radiation is very ionizing, meaning it interacts a lot with the surface atoms of anything it hits. So much so that the alpha particles get completely stopped by as little as a sheet of paper or a couple of centimeters of air. They are not at all penetrating because of how much they ionize or interact. What with each beta particle having a size 1 charge, beta radiation is a bit ionizing, meaning it interacts a bit with the surface atoms of anything it hits, but not as much as alpha, so beta is more penetrating. Beta is stopped by 2 or 3 millimeters of aluminium. Gamma radiation doesn't carry any charge, so gamma is not ionizing. In other words, it does not interact with the surface atoms of things it hits. Because of this, gamma penetrates very deeply into materials, and there has to be 2 or 3 centimeters of lead shielding in order to get this not very ionizing at all radiation to stop. So the top picture here is showing those minimum materials and thicknesses required to stop the different kinds of radiations, as we've already talked about. Next, we look at some uses of these radiations. Gamma is used to treat cancerous growths, usually when the tumors are deep inside. Because gamma is not ionizing, it doesn't tend to interact with atoms, so gamma gets deep enough to reach the tumor. This is called radiotherapy. Beta radiation is used in situations where you want some radiation to get through, but not all. This lets paper mills control the thickness of paper, and lets toothpaste and facial cream filling machines fill the tubes to the right level. Finally, alpha is used in smoke detectors, because we want a radiation that gets completely blocked by smoke. Alpha does get blocked by smoke, so can't ionize the air molecules, and so free electrons stop getting to the detector. There are heaps of uses of radiation. If you're asked to comment on a use, have a think about whether you want radiation to pass through something, or be stopped quite quickly. Because that will decide whether alpha, beta, or gamma is used. Physics is a quantitative subject, which for us here, means that we want to be a bit more accurate than saying a lump of something is either very radioactive or only a little bit radioactive. The level of radioactivity of a material is usually just called the activity of the source. The source just being the object that is radioactive, by the way. The formula we use says that the activity of a source is the number of radiation particles spat out by the source, divided by the time over which the counting is happening. Many radiation particles out every second from this object means that the object is very radioactive. The radiation spitting out process is also known as nuclear decay. So the formula is also commonly given as number of decays divided by the time. Also, the shortened version of the formula, which is on the formula sheet, is pretty logical. Capital A equals capital N over lowercase t. Activity is given the units becquerels, named after the French person who discovered radioactivity. So here's an example. We are asked to calculate the activity of a source which has 5,000 decays in 8 minutes. The first step, as ever, is the shopping list. Activity is what we're trying to find, so that's question mark. We're given N, and we're given T, though we have to turn it into seconds. Then, we find and copy out from the formula sheet a likely-looking formula that has the letters in the shopping list. We put the numbers into it, do the maths, and remember to include units with the final answer. Next, calculate the number of decays that happen in 20 seconds in a source with an activity of 40 kilobecquerels. There's the shopping list. We've remembered to deal with the prefix, replacing the kilo with times 10 to the power 3. Here's the rest of the answer. After copying out the formula and putting the numbers in, we might find that we need a triangle. That's okay, draw one out. This then tells us how to carry on to find N. The answer is just a number, and there aren't any units. If we have a lump of something radioactive, will it keep on giving out radiation particles forever? I'm afraid not. Once an atom has fired out radiation, that's it. It won't do it again, it's a one-time event. And because the radioactive lump has a fixed number of atoms, the radioactivity of the lump will get smaller and smaller over time. The shape of the graph of radioactivity is always a downwards curve, like this. There's this idea of the half-life time of a radioactive material. The half-life time of a radioactive material is the time that it takes for the radioactivity to fall to half of its starting value. Why don't we use the time it takes for the radioactive lump to stop being absolutely completely no longer radioactive at all? Because for some sources, they take so long to decay that waiting the full time would be billions and billions and billions of years. So the half-life time is more of a practical measure. To find the half-life time from an activity graph of a material, see what the starting number is. Halve that starting number, so for here, the starting number is 120, so half of that is 60. Go across at 60, then down to the time axis once you've hit the downwards curve. The number at this point on the time axis is the half-life time for the material.